Yeah.
Good morning. Uh, so we continue with Matthias Flach telling us about special values of motivic L function, the second talk, and hope we have a good day.
Okay. So good morning, everyone. Um, I won't be saying many new things today, so I will repeat the fundamental line. So in case you have never seen this before, I thought it might be useful to just see it all over again. Um, as but now in full generality. So I will talk about these period and regulator maps for a general motive over Q and how you use the fundamental line to make a special value conjecture. Okay, I guess I can use my clicker, so yes. So the setup is, as yesterday, we talk about smooth projective varieties over Q rather than arithmetic schemes. And we talk about cohomology theories, which are functorial not only under morphisms, but under correspondences. So in other words, any cycle in the Chow group of x cross y will give you a morphism from the motive of x to the motive of y. And it's kind of an empirical observation that there are many idempotent correspondences. For example, there should be idempotents which cut out the individual hi in the total motive. And this is known for curves and surfaces, but not in general. So you take such an irreducible summand, cut out by correspondence, and to this you attach an L function and all the data I'm going to talk about. So if you like, you can talk about Wojewodsky's category, but this is really irrelevant for this discussion. In particular, we don't know that Wojewodsky's category has a motivic T structure. And the objects M I'm going to talk about should be thought of as lying in the heart of dm in some abelian, actually semi-simple category of motives. If you just take projective varieties, the category should be semi-simple. Another thing about motives is that the same motive occurs in many different varieties. For example, the motive of a point, Q0, occurs in any variety as the H0, if the variety is connected. So this motivic formalism is kind of already a bit removed from geometry. It's linear algebra. Okay, so we only need a naive notion of motive given by this motivic structure, which is all the so-called realizations. So you have the L-adic realization, which indicates that M is HIXJ. So this is my standard example for a motive HIXJ. In this case, you just have the ith et al. Cohomology of X extended to Q bar with QL coefficients, and this has a Galois action just by functoriality acting on Q bar. And then you have the Betti realization, which is the singular cohomology of your variety of complex points of X. As was discovered by Deligne, this has more structure than just a Q vector space. It's a Q hot structure, which means if you tensor with C, you get a bigrading on this space, and J just shifts the grading. And then you have the de Rham realization, which is a filtered Q vector space. And all these spaces are in some sense the same cohomology theory. In particular, they have the same ranks, or even better, they have comparison isomorphisms between them. So there is an isomorphism going back to Artin. In the early development of et al. Cohomology, he compared the L-adic cohomology with a complex Betti cohomology after you tensor with QL. So that's what this sub QL means. You have the Betti-de Rham period comparison isomorphism, also standard going back to Grothendieck, if you tensor with C. And then you have Fontaine's conjectured, now proven in many ways, isomorphism, which is the p-adic analog of the period isomorphism. But then you have to take this p-adic period ring B de Rham. I don't know. It hasn't occurred in the conference so far, but I'll just leave it as a black box. For the purposes of period isomorphism, it's the p-adic analog of the complex numbers, but it's not CP. It's a certain complete discrete valued field with residue field CP. Okay. So you have this realizations, and then you have an L function attached to the motive. So the Euler factor of the L function is given by the characteristic polynomial of a geometric Frobenius. So it's the inverse of a lift of the P's power maps inside the Galois group. So remember, on ML we have the action of the Galois group, and in there you have Frobenius elements because the action is actually unramified outside a finite set. And and it acts not quite on the L-adic cohomology, but you have to take inertia invariance because only the Galois group of the residue field will act. I mean, the Frobenius lies in the Galois group of the residue field. And so at bad reduction primes, this is a non-trivial operation, taking invariance or under inertia. But at good reduction primes, by standard base change theorems for L-adic cohomology, this ML is also just the L-adic cohomology of a reduction mod P, and then it's just the action coming from the finite field situation on this ML. So I put a question mark. So this is supposed to be independent of L and have rational coefficients, and that's not known. I mean, it's known for good reduction when inertia acts trivially, but if in general, if you have non-trivial inertia invariance, this might depend on L. But yeah, so you have to define this rational factor L-adically, and your conjecture is independent of L. So you have a rational polynomial, you plug in p to the minus s, and you make the Euler product, and that's the L function. So for example, if you have an h1 of an elliptic curve, this is a degree 2 polynomial, and you have this degree 2 Euler product. This p is a prime. All primes, only the finite primes. Oh, you mean which p? Yeah. A polynomial capital P depending on a prime little p. So this is only a product over the finite the actual prime numbers, right? And this L is different from P. Yeah, so you take a because you want to relate this to L-adic cohomology over finite fields in the good reduction case, where this is known to be a polynomial independent of L, right? By standard work on L-adic cohomology by Grothendieck, Deligne, and so on. Okay, examples. If you take a Tate motive over a number field, you get a shift of the Dedekind zeta function. As I said yesterday, there's no distinction between the arithmetic scheme point of view and the motivic point of view in this zero-dimensional example. So there's only an H0. If you take a motive of a number field like the Gaussian numbers, you can decompose it under this Galois action into two irreducible pieces. So it has the unit motive as a summand, and it has another Artin, so-called Artin motive attached to the quadratic character associated to that number field. And I also mentioned it yesterday. That's a Dirichlet L function. So you can make the same thing for any number field. You get so-called Artin L functions for non-abelian characters as well. Another example would be an elliptic curve. In this case, it has Cm, at least if you base change this E to the Gaussian numbers. I mean, you can see the Cm here. If you multiply y by I and x by -1, you get an endomorphism or automorphism of this equation. So it's a Cm elliptic curve. And its L function of the H1 is actually a Hecke L function. So that's a very non-trivial example of this connection I had on the board at the beginning between motivic and automorphic L function. So this is actually an automorphic L function for GL1 over this imaginary quadratic field. And it can be identified with the L function over Q of this E, which is defined over Q. Over Qi, you would get two factors of phi and phi bar, but over Q, it's just this. And this is a very concrete object. It's a character on the ideals of this field, given on principal ideals by this recipe. So again, this is all much studied in number theory, but maybe only of peripheral interest to this audience. But there's lots of concrete number theory behind these things. And here you have a non-Cm elliptic curve where the L function is attached to weight 2 cusp form. So if you've never heard this, I'm not going to say more about it. It's very classical 19th century mathematics. You have this notion of modular form on the upper half plane, and that's what this F is. Yeah. Well, I mean, for an elliptic curve, the H1 has a quadratic Euler factor, which is just the L function of the H1 of the elliptic curve over a finite field, kind of, at least at good reduction primes. Oh, yeah, the H1 is, so you get rid of the H0 and the H2 of the elliptic curve. It's just the H1 part. So that means the realizations of this H1 will just be the H1 here. In each degree you have the H1, rather than the total cohomology of E. Oh, this is just referring to Vojevodsky's category, the geometric motives, as he called them. So he has a category of geometric motives which he embeds fully faithfully into these Nisnevich schemes with transfer and homotopy invariance. But all of this is irrelevant. So there is some triangulated category of motives. If you like, you can view this M as an object in there, but it's not relevant for this discussion. In particular, the T structure is not known, so you only have a triangulated category, which we don't want. We want an abelian situation. So, okay. So these are classical examples of L functions that you can prove have a nice analytic continuation and functional equation because they're related to automorphic L functions. So this curve has conductor 37, so that's why it's associated to a cusp form on X naught 37. That is a certain algebraic curve, a quotient of the upper half plane. So I'm just leaving this as a black box for now. Okay, so in general we expect that these functions have a meromorphic continuation, which means that, well, like in complex analysis, they continue to all complex S, and they have a functional equation which looks like this. So you have to complete the L function, which was a product over the finite primes, by a product over the infinite places, by this infinite Euler factor here, which depends on the Hodge structure. So the H, P, Q are the Hodge numbers in the Hodge structure associated to your motive. And then you have these gamma factors defined very explicitly by this recipe, and you make this product, and here P does not denote a prime. P is just an integer. It comes from this PQ bigrading of the Hodge structure. Oh. Yeah, this is the eigenspaces of Frobenius. So if you go back to the Betti realization, you have the complex conjugation, the infinite Frobenius acting on here, even with Q coefficients, and you take plus and minus eigenspaces. I mean, it visibly acts because it acts on the complex numbers. Okay, and yeah, PP. I mean, this is PP, the PP case. In this case, it does. Yeah, it's the PP plus space. Yeah, yeah. I mean, otherwise, it will exchange PQ with QP. Yeah. Yes, that's what it means. Yeah. Okay, so there is some dual motive, which on linear algebra, it's just taking the dual spaces of all these realizations I was talking about, and it can be realized in the cohomology of your variety at a different degree by Poincare duality. So the dual motive is also a geometric object, but we can also just view it in terms of linear algebra as the dual space of all these realizations. So when is this known? Again, for low-dimensional cases, I mean, the H0 for any x is just the H0 of the global ring of functions, which is a number field for a smooth projective variety, or a product of number fields if the thing is not connected. And so in this case, we reduce to Dedekind zeta functions. Again, for an elliptic curve, it's now known quite a number of cases. I mean, now meaning in the last 30 years or so. So almost exactly 30 years ago, the Wiles proved the case F equals Q for semi-stable elliptic curves. Famous breakthrough at the time. And by identifying exactly any E can be identified with a weight 2 cusp form, so that's what he did. So that's the H1 of X for an elliptic curve over Q. And then people have pushed these automorphic techniques to other number fields. So in particular, modularity, as it's called, for elliptic curves is known over real quadratic fields or cubic fields. If you only want potential modularity, as people call it, that leads to meromorphic continuation, this is known over any totally real LCM field. Proven by many people, Taylor, Wiles, Clausel, Harris maybe. It's known for this curve, that's the Fermat curve. So this is a projective equation in P2, defines a curve, and it's called a Fermat curve because it's related to the Fermat equation. And what's special about this curve is that it has many endomorphisms. If you imagine Z1, Z2, Z0 being the coordinates, you can multiply that with arbitrary nth roots of unity, and that gives you complex multiplications of the Jacobian or the H1 of that curve. And so because it has lots of symmetries, you can reduce the L function of that curve to Hecke L functions, as it turns out, over cyclotomic fields. And for Hecke L functions, we know continuation and functional equation. So that gives another example where this picture is known. Now for higher symmetric powers of elliptic curves, so this is just the symmetric power in the sense of linear algebra, right? So this H1 is a two-dimensional space in all the realizations, and you take its symmetric powers. And this is again a motive. It occurs in some cohomology of some variety. In fact, in the n-fold self-product of E, it's a direct summand of this. So it's again a motive occurring in some variety. And meromorphic continuation is also known in this case by Taylor and Clausel and others. And then for many Shimura varieties, I'm not going to be precise. So Shimura variety is like a modular curve. It's a quotient of some Hermitian domain by an arithmetic group, and it turns out to be an algebraic variety over a number field. And the middle degree cohomology can be expressed in terms of automorphic forms, and then you also have these properties. So all proofs go via automorphic forms whenever this is known. Yeah. Yes. But only very slightly different. I mean, okay, I want. Yeah, okay, the question came up. This normalization of the gamma factors is different from Deninger's normalization. Of course, I cannot record out of my head Deninger's normalization, but okay, yeah, right. So I want gamma C to be the product of gamma R of S times gamma R of S plus 1. So it's like some induction formula, right? I mean, in general, if you have a motive over a number field, you can always view it over Q by some induction, and the same thing happens at infinity. So you want gamma C to be gamma R S times gamma R S plus 1, and that's why you have to put the 2 in there. Yeah. one half on the other side, yeah. Okay, so don't nail me down on the precise normalization, but you definitely want that property that gamma C behaves well under induction. Yeah. So it's just a recipe depending on the hot structure. I mean, it's completely different from the finite Euler factors, but I'll come back to these factors when we discuss arithmetic schemes tomorrow, or actually Thursday probably. Okay, so now how do we get at the special value? So in addition to these realizations, Betty, Dara, Maladic, we need another set of groups attached to M, which is motivic cohomology of M. And again, these are just Q vector spaces, just like the realizations, so everything's rational. So Chow groups have been briefly mentioned already at this conference, and so these are generated by algebraic cycles of codimension J in X. It's just a free abelian group by some relations on these cycles, and any cycle gives you a cohomology class in singular cohomology. You can physically imagine it giving you a cycle in, if you triangulate your subvariety, there's your closed subvariety of codimension J, you literally get a class in singular cohomology, at least the Poincaré dual of such a class. Yeah. So you have the cycle class map, and it's very mysterious which classes in the cohomology actually come from algebraic cycles. So that's the content of the Hodge conjecture. But whatever it is, this map has an image and a kernel. So the image of the cycle class map we declare to be the H0 of M. Again, if M is this H2J twisted J, for other M the H0 is trivial. Another way to view this is that if you have an image of a cycle in here, it generates a copy of the unit motive of Q0 inside this H2J J, right? So that's another way of viewing the cycle class map. So you get a certain, because everything is semi-simple, you get a certain number of copies of the unit motive in this H2JJ. That's a certain vector space. So the dimension of H0M is just a number of copies of the unit motive in M. And then you have the H1 motivic cohomology of M, which you just define by this recipe out of the K theory, the rational K theory. So if M is HIXJ, then you take this K group, and the upper J means Adams eigenspace. So you have Adams operators, because you tensor with a Q, everything splits into eigenspaces. So on this eigenspace, psi K operates by K to the J. And that's also motivic cohomology in terms of higher Chow groups, but let's just leave it as a K group. Everything's rational. And in this particular case where 2J minus I minus 1 is 0, so then you have a K0, but you don't take the full weight J piece of K0, which would be the full Chow group. You only take the kernel of the cycle map as a piece of H1. The other piece is in the H0. Right, so that's just a definition, and now we have to modify this slightly. We have to look at the sub F groups. It goes back to Bloch-Kato. Sub F means something coming from an integral model, right? So even though we only talk about varieties over Q, you just wouldn't get a correct picture if you ignored some stuff coming from an integral model. And so this was defined in a very roundabout, weird way. So you just take the H0 is the same for the integral model, but the H1F is the image of the K theory of some regular proper model. And you can show that this image in the rational, in the K group of X, is independent of the regular model. No. So, but if you're in this setup, you can actually use alterations of de Jong, and the image will exist independent of a regular model. So this H1F is defined at least independent of existence of a regular model. But this is clearly very non-canonical, and we certainly should work with X directly, which is what I'm going to talk about tomorrow. Okay, so but that's what people did, and so now we have the period isomorphism. It induces a map just by taking invariance under complex conjugation. So I already mentioned that complex conjugation acts on the Betti even rationally, so it acts on M Betti C, and you take the plus space, so the rational plus space tensored with R sits inside the invariance here, and then you take Galois complex conjugation invariance on the de Rham tensor C. It just gives you the de Rham tensor R, and then you project into the quotient modulo field 0. So you have this modified period map, and this is really the part of Deligne cohomology attached to this particular M. Yeah. So the kernel and co-kernel of alpha m is some H0 delene and H1 delene attached to M, and I will come back to delene cohomology tomorrow. But it's just a thing that works. So it's this modified period map. And then we have this big assumption that everything is finite dimensional. So these rational vector spaces defined by this regular model or by alterations supposed to be finite dimensional, which is the big unknown in all of this picture. So if you knew finite generation, you would be much further. But we have to put it in as an assumption, and it really only holds in very few cases. I mean, it's known in very few cases. Yeah, for the rational K groups, yeah, should be. Yeah. Okay, so then we should have this 6-term exact sequence involving the co-kernel and the kernel of alpha m. So this is like some H0 delene and H1 delene, and you have a map from the motivic cohomology of M. It's somehow a localization map to the Archimedean places. So on H0 we get the cycle class map, so you can see that the kernel of alpha m is just the cycles which lie in the fill 0 of the de Rham, but the fill 0 here was just the fill j. So this is the Hodge condition on your cycles, right? So if you say something in the kernel of alpha m is a cycle that satisfies a class that satisfies the Hodge condition, it lies in the fill j here. And conjecturally, that should characterize the cycles, at least tensor R. So that's this part of the sequence. And then we go on. We have a height pairing between the H1F of M star 1 and M. So only for very few M's is both M and M star 1 non-trivial. So if you take the H11 of an elliptic curve, that's where it happens. So you have the points of an elliptic curve here. That's what the H1F would be in that case. Because it's this child 0 group, and on that you have a height pairing. So if your motive has what's called weight -1, this might be non-trivial. Otherwise, this space is 0 most of the time, if this is non-zero or vice versa. And then you have the valence and regulator map from this motivic cohomology H1F into the H1 delene, or the co-kernel of alpha M. So again, this C and R together is some kind of localization map of motivic cohomology of the global scheme to the local Archimedean motivic cohomology, which is the lean cohomology. And so you have this exact sequence after you tensor everything with R. Yeah. Well, the maps are known to exist. Yeah, the exactness is conjectural. Yeah. 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 Well, I mean, you can take this map to just be the dual of R, right? I mean, whenever this is, yeah. So I mean, you take, yeah, this is the dual of R. There is a duality for delene cohomology, so this would be also the co-kernel of alpha M star 1. Yeah. Yeah, so it exists, the maps exist, but yeah. I mean, another way to view this sequence is, okay, so we have this localization map from global motivic cohomology to Archimedean motivic cohomology, and then we take the mapping cone and we define some compact support motivic cohomology, right? And then what this really expresses is a duality between compact support and the ordinary motivic cohomology. And this point of view I will come back to in the arithmetic scheme context tomorrow. So, yeah. This here. Yeah, okay. So remember, M de Rham was a filtered vector space. So that's just a fill 0. Yeah, yeah. But remember, M might be shifted. So if M is this, then it's actually the Fj on 2H2j, right? So what I call fill 0 would be a fill j on the 2j cohomology. Yeah. You mean if every point is conjectural, or if it's known to be exact? Yeah, it's known to be exact here, I think. No, because this is defined to be the image. Yeah, I mean, okay, basically no. Yeah, I mean, what's happening is that for a given M, many groups are zero, right? So very often you just have a this is the only non-trivial map in this. Yeah. So for example, if I take M to be of weight minus, yeah, I mean, if I take the zeta function of a curve at s equal 2, 3 or higher, then this is the only I mean, if I take h1 of a curve and j is bigger than 1, then this would be the only non-trivial part of the whole sequence. So in practice, lots of terms collapse for a given M. Yeah. Okay. And okay, so let's put faith in that and assume this exists. And now we can describe the vanishing order of the L function. So remember, we had our L function, and by Tate twisting, we can always just reduce to s equals 0 because we can replace M by M twisted J. So let's do that, and then we want to compute the leading Taylor coefficient and the vanishing order of this meromorphic function. And by because this Euler polynomial here had coefficients in Q, that means if you evaluate this L function at a real number, you get a real number. So the leading coefficient is actually always, is always a real number. So the leading Taylor coefficient is in R, and of course the vanishing order is some integer. And the vanishing conjecture says that the vanishing order is just this Euler characteristic of the H1F of the dual, or coming back to that explanation, you could also view it as some compact support homology of M itself. And but that's how Fontaine-Penriou formulated it directly. So because, yeah, it's just that. And it's known again for the Dedekind zeta function for any j, because yeah, you just look at it by inspection. So you look at s equal 1, for example, was already on the board yesterday. The H1F is trivial because M star 1 of Q1 is Q0. It doesn't have an H1F because the relevant K group would have negative index. Yeah, so this is trivially 0, and then if M is Q1, M star 1 is Q0, so you have an H0 spanned by the cyclic class of a point, so we just get -1 here as the vanishing order, which is the pole at s equal 1. And at negative integers, you have a vanishing order determined by the gamma factors, and you just look by inspection, you compare it with Borel's theorem that gives you the ranks of these groups, and they coincide. So another important remark is that the ranks of these motivic homology groups, like in this example, they're completely determined by the gamma factors, except the ranks of this H1F when there's a non-trivial height pairing. So the only mysterious ranks, really, so like the rank of an elliptic curve, they occur if you have the non-trivial height pairing, but in the generic situations, everything's determined by this co-kernel of alpha M, whose rank is easy to compute. So the rank of the motivic homology is no mystery if this sequence reduces just to this being an isomorphism. So everything's determined by Archimedean data except for if you're at what's called the central point of the functional equation. Then the rank is mysterious. Okay. So what else is known about vanishing orders? Well, we know a little bit about elliptic curves over Q, but only if the rank is at most 1. So, I mean, the vanishing order or the rank of the group of points. For higher rank, absolutely no information is known. And the reason we know something is because of special formulas like the Gross-Zagier formula and things like that, which I'm not going to say much about. But so in that case, and the proof is complicated. I mean, it's not at all straightforward. but you know if the L function doesn't vanish, if the vanishing order is 0, you know that the group of points is finite, so it has 0 rank. And you know the same if the vanishing order is exactly 1, the group of points has rank 1 of an elliptic curve. But the proofs are highly non-trivial. And then for an individual example, you can numerically check that that sometimes you have a curve of rank 2 or 3 and the vanishing order is also 2 or 3. So for individual examples you can verify that, but not in any generality. I mean, that's about it, because we don't know finite generation in most cases, so we cannot verify the vanishing order conjecture. But in these cases we can. We know finite generation by the Model-Way theorem for the points of an elliptic curve. Okay, now we come to the actual leading coefficient. So that's the vanishing order, and now we want to describe this leading coefficient, which is a real number. And yeah. 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 Well, that's just an experimental fact. Why is that? Because a number field has kind of small arithmetic dimension, well, everything's over the base Q, right? So a motive is kind of pushed forward from X to Q, and then over Q we only have X0 and X1. Yeah. Yeah. So I mean, it's reflected, for example, in L-adic cohomology that you only have an H1F and an H0F. So you can rigorously define the L-adic analog of this HIFs, and there you can rigorously prove you only have H1 and H0. I'll actually come to that in one form or another. I have to come to that. So here we see the fundamental line again, like in yesterday's talk. So this is now a rational vector space given by taking the determinants of all these Q vector spaces appearing in this sequence here, right? So we had the Betti plus space was a Q vector space. The Ra modulo field 0 is a certain Q vector space. We had these 4 motivic cohomology spaces, and after you tensor them with R, they're all related by these sequences. So that means this fundamental line, after tensoring with R, is trivialized by this exact sequence. So that means we have this isomorphism theta infinity. And the special value conjecture would say this real number, which lives in here, lies in this rational subspace. So that takes care of all periods and regulators in your special values, miraculously. And so if you like, you can view this trivialization as coming from the duality pairing between compact support motivic cohomology and motivic cohomology of the dual somehow. Or for an elliptic curve, it would be the height pairing, which gives you this. Yeah, so it's induced by this exact sequence, which are called conjecture mod infinity. Again, it's known for number rings by Borel's theorem. So remember, Borel's theorem had several parts. The part he proved last was actually a rationality statement. So the zeta function at S equal n for positive n is some regulator up to rational factors. But the regulator was very complicated and inexplicit, and there's a theorem saying that the Borel regulator is actually the same as the Bailenson regulator, which appears in our sequence here, up to a factor of 2. Okay, so people have looked at this really precisely. Okay. When is this rationality known? Well, again, in the cases I mentioned before, basically things coming from a Shimura curve, which is a modular curve in the case F is Q, and the Gross-Zagier formula gives you the rationality part as well. So the Gross-Zagier formula will relate the derivative of this L function with the height pairing of a particular point on which you construct for using this Shimura curve, which has a map to your elliptic curve, or on the level of Jacobians, can also argue with that. So when else is it known? Not in many cases, because again, we don't know finite dimensionality. So it's a weak version of it is known, and I'll come to that in some cases. Okay, here's a fun example, an example where this fundamental line is actually canonically Q. So what does that mean? It means that all these spaces in this determinant are actually zero, right? So if you have zero here everywhere, the determinant of zero is canonically the coefficient ring. So when in this formalism of determinants of perfect complexes, that's kind of built in, an acyclic complex or zero has canonically determinant the base ring, which is Q. And so if all these spaces are zero, psi m is canonically Q. And what that means is, of course, that the zeta value is a rational number. And that sometimes happens. I mean, it's extremely rare, but it happens for a totally real field and negative J. For example, if f is Q, then you have this formula for the Riemann zeta function in terms of Bernoulli numbers. It's just a rational number given by this generating series. So everything's totally concrete in that case. And it's known for totally real fields as well by the Kling-Siegel theorem, but I'm not sure there is an easy recursion for these numbers in this general totally real case. Only for abelian extensions of Q where you have a similar formula. Okay, so so that was one of my main advertisements for this point of view of Fontaine-Penriou with a fundamental line, that it really covers all integers. I think that's very important because to get at the whole function, you want its values as many values as possible to say something meaningful about. Okay, so that works as well. And now we have to describe the unknown rational factor, right? So the rationality statement just means we pin down this real number. We know it's in here, but that's a one-dimensional Q vector space, so we know this number up to an unknown rational factor. And how do we pin down the rational factor? So that involves Galois cohomology. So we now look at the analytic realization, which is a Galois representation both of the global and local Galois group. And so we have to define the analytic analog of this F cohomology over a local field. So we fix a coefficient prime L, and then for any other prime, we have this F cohomology locally. If L is different from P, it's just the unramified cohomology. So this would be, if you like, you view your sheaf as an étale sheaf on spec ZP, and you pull it back to the closed point. That gives you this inertia invariance, and then you take its cohomology over the finite field. So that's this F cohomology in this case. It's just the unramified cohomology. And in the case where L is equal to P, I have to again refer to some black box concepts. I have to refer to Fontaine's functors d Chris and d de Rham. So d de Rham is just a way of getting de Rham cohomology out of L-adic cohomology by the comparison isomorphism, right? So remember we had this comparison isomorphism of L-adic cohomology with de Rham cohomology over a local field using this ring B de Rham. And so if you tensor ML with B de Rham and take Galois invariance, you get de Rham cohomology. So that's a functor on L-adic representation that you can make for any L-adic representation. And that's d de Rham. So it's again a filtered vector space. And d Chris is using another ring B Chris, and you'll get a vector space with a Frobenius, which would be the crystalline cohomology of the special fiber in case you have a smooth proper model over the integers. Okay, so that was the key insight, that you have the analog of F cohomology, and you can define it in terms of Pierre-Descartes theory. So if you like, this is symptomic cohomology of MP. It's another way of viewing it. It's all rational though, with QP coefficients. Okay, so the F cohomology, the cohomology of the integral model, if you like, maps into the cohomology of the generic fiber, which is just Galois cohomology. And you define mod F to be the mapping cone. And then you make similar simple modifications of the global Galois cohomology. So you have globally the compact support cohomology is just defined as the mapping fiber to all local fields for the primes not in S. And you define global F cohomology as the mapping fiber to all these local mod F cohomologies. And then combining these two triangles, you get a global triangle expressing R gamma C in terms of R gamma F. So again, this F is a somewhat awkward way to bring in an integral model, even though we only have motives over Q. It's, if you like, in the theory of perverse sheaves, this would be an intermediate extension from the generic fiber to the ring of integers, something like that. Okay, so we have now in the L-adic world, we have this F cohomology, and we want to relate it to the motivic world. So again, you have from the motivic cohomology, there were these rational vector spaces defined in terms of K-theory I introduced before. After you tensor them with QL, they're related to these L-adic spaces I defined on the previous slide. So this isomorphism would be a form of the Tate conjecture. It would mean that the cycles are just the Galois invariants in the L-adic cohomology. Yeah, so that's the version of the Tate conjecture for any motive. And similarly, for the higher K groups, you have Chern class maps from K theory. And so this was, remember, the K group of some integral model or its image in the generic fiber. And conjecturally, this should be definable entirely in terms of Galois cohomology for following this model here. So that's another conjecture that after you tensor with QL, you get this Galois cohomology construction of H1F. So you can show there's a duality like this for the L-adic H1F. And so this conjecture then computes the R gamma F complex in all degrees. So for 0 and 1, you have this Chern class map, and then for 2 and 3, you have the dual of a Chern class map. Oh yeah, so here at the infinite places I take ordinary cohomology throughout. Oh. Yeah, but it's a duality between R gamma C and R gamma, whereas here I have a self-duality of R gamma F. And everything is with rational coefficients anyway, so you don't see. It's all rational. Everything I'm saying in this talk is all rational. So you might wonder, how do we pin down this number? But I'll come to that. It's all rational vector spaces. Yeah. So the cohomology at infinity. So if P is infinity, I just take the invariance. It's just the invariance and nothing else. Yeah. So I can't repeat that enough. This whole picture is starting with rational vector spaces, producing rational vector spaces. I'll say in a minute why we can describe the L value precisely. Okay. So these are rational conjectures. There's a QL vector space, that's a QL vector space, and same here. Yeah. Yeah. But then you have to modify it to bring in this F cohomology. So Poitou-Tate would relate R gamma C and R gamma, would be dual to each other, and you want a self-duality of this R gamma F. And yeah. And that boils down to the fact that under the local Tate duality, this R gamma F is self-dual, right? Yeah. I mean, there has been a reworking of this in the prismatic world where you don't have to rationalize. I think this is now by Butt. I saw some lecture notes where you have has a similar triangle but with integral coefficients. And as I said before, this is symptomic cohomology but rationally, right? Rationally, symptomic looks like this. Okay. And so now this is kind of the analog of our mod infinity conjecture. So we we relate the global motivic cohomology with some allatic versions defined entirely in terms of Galois cohomology. And now we take our fundamental line and tensor with QL, and we don't get a trivialization. It's not isomorphic to QL, but to the determinant of this R gamma C, which occurred in this triangle, right? And well, you can kind of see how the terms in the fundamental line appear. The global motivic cohomology all appears in here by this conjecture, by this one here. Yeah, so that takes care of the global motivic cohomology in the fundamental line. And then locally, you have the de Rham appearing in here, and you have the Betti plus space appearing at infinity here, and that's why everything appears more sooner or later in the fundamental line. So that means the compact support cohomology contains all the terms in the fundamental line, and you get this isomorphism. Now, okay, so given that, how do we define a precise Z lattice in here? Well, we take compact support cohomology for any ZL lattice in this QL representation. So remember, ML was just an aladic QL representation of the Galois group. Take any Galois stable lattice, which of course always exists because the Galois group is compact, and take its compact support cohomology, and then it's a little lemma that the determinant of this as a subdeterminant of this doesn't depend on TL, which means if I take a finite Galois module, then this compact support cohomology has Euler characteristic 1, multiplicative Euler characteristic 1. So that boils down to Tate's formula for the Euler characteristic of a finite Galois module. And so in this determinant context, it means that this rank 1 ZL lattice in this QL vector space is independent of the choice of TL. And it gives me a ZL structure on here, and the special value conjecture says, well, the ZL structure is spanned by the L value again. So it's pure Galois cohomology. This is why we can pin down this rational number up to sign. Yeah, so for any prime L, this pins down the aladic valuation of this unknown rational number, and putting all primes together, all L, we determine the number up to sign. Yeah, good question. I mean, whenever you have a 0, it changes sign, and if you're very positive, it's positive. So you can try to work from there, but it's, yeah. But I don't know a systematic conjecture about the sign. Yeah. Yeah, I'm really running behind a lot because I was going very slow. Yeah, that's good. So now everybody has seen the fundamental line again. And you can also show it's independent of the choice of this S. So if you increase S, well, you pick up more Euler factors, so you have more unramified primes where the F cohomology looks like that, remember? So you pick up more terms here, but then you trivialize the F cohomology by the identity map here. There's a little subtlety, so you kind of get rid of the Euler factors in S, and you verify it doesn't depend on S. Okay, let me not say more about this. Yeah. Oh, you mean as a Galois representation? No. Okay, so again, so when is this known? As I was hopelessly trying to explain yesterday, it does recover the analytic class number formula. If you really unwind this R gamma C using this triangle, etc., you find all the terms in the class number formula. So this is the only case that's proven in any generality. Now for higher Tate twists, including negative ones, we do know the full conjecture for abelian extensions of Q. So in other words, subfields of cyclotomic fields. So at the very beginning, I promised you that everything is known for Dirichlet functions, and indeed it is. And that's because of Iwasawa theory. So we can prove everything for abelian extensions of Q, which at least is good to have some evidence outside the classical cases. And you can push this a little bit to abelian extensions of imaginary quadratic fields. because you have similar structures there. I mean, the key fact why you can prove something is you have explicit units, the so-called cyclotomic units in cyclotomic fields. And the same thing happens for these fields. We have so-called elliptic units. And that gets everything going. And then the Bird-Swinnerton Dyer formula, which is exactly what you get for this motif. So whenever you have an elliptic curve or a abelian variety that is equal 1, so you have H11, you get BSD. And there has been lots of work on BSD for elliptic curves over Q. At least if you work outside a finite set of bad primes for the coefficients L, then you have a proof of BSD. So certainly for many CM elliptic curves, so this is now known even without an exceptional set. And then for a semi-stable elliptic curve over Q, by lots of work, first Kato, then Skinner-Aubin, you do actually have the BSD formula. So you know finiteness of Shah, you know the BSD formula. But again, still with some exceptional set for a non-CM curve, I think. In general, for particular examples, you can verify it for all primes. But okay, so that's a BSD case where people have done lots of work because it's very classical. And but outside S equal 1, if you look at the L function at higher S, you only have very weak statements. And now I wanted to say a little bit about the equivariant refinement. Maybe I'll skip that. I mean, the basic fact here is that you have your motive, and we always viewed it with coefficients in Q, right? But very often you have extra symmetries. You have some semi-simple algebra acting on your motive. For example, for an abelian variety, you have this endomorphism ring as an abelian variety. In the CM case, this could be a CM field, for example, or it could be any kind of other semi-simple algebra. And then you want to do everything equivariantly over your symmetries, over the endomorphisms. Or you have some finite group acting on G, which occurs all the time. For example, you simply take a Galois extension, you base extend some X prime to a Galois extension, and then you have the group ring acting on your whole motive. And you can carry through this whole formalism I was explaining, throwing in everywhere A where I put Q so far as the coefficients. So let's say A is commutative, so we don't have to worry what determinants mean. Then a semi-simple Q algebra is just a product of number fields. And all the quantities and isomorphisms I was defining, you just do over A instead of over Q. So the L function would be A tensor C valued. So it's a tuple of L functions indexed by the embeddings of A into C. Yeah, so it's a vector of L functions that you describe by this formalism. So it's very much a refinement of taking the product of all these L functions. And the vanishing order would be a locally constant function on spec AC. So it's a tuple of integers indexed by the embeddings of A into C. And the leading coefficient would lie in A tensor R. So everything goes through. And your isomorphism would now trivialize the fundamental line to the base ring A tensor R. You have the isomorphism with compact support cohomology, which is now an AL module. I'm just repeating everything I said, putting in A everywhere. And then integrally, you have to make a choice. So with Q coefficients, we had to take a Galois stable ZL lattice. Now you also have to pick an order in your semi-simple algebra. And you have to take a Galois stable A tensor ZL lattice. Yeah, so for example, in this group ring case, you could take the integral group ring. This is free over the integral group ring, so it's certainly projective, and you have a conjecture. And it's actually true in this Dirichlet case, for example, which is quite remarkable because the rationality conjecture in this equivariant setup is not even known in the class number case. So this is what people call Stark's conjectures. So this equivariant finer L function where you bring in the Galois action on the number field and you look at this vector of Artin L functions is not even known rationally for the class number case. there's still something to do there, and you can do the same with non-commutative coefficients. So maybe this I'll skip. So I don't have to assume that A is commutative, so I can do everything using determinant formalism non-commutatively. And so this is now what people call the weak Tamagawa number conjecture, where you don't know finite generation. I guess I have to conclude now in some way or another. So let me just say that this equivariant conjecture over the group ring, so here you just take a motive and you extend with some Galois extension, and let's take a Tate motive over Q, and you take an abelian Galois extension, so again we're back to cyclotomic fields, then this whole equivariant formalism over ZG is also known, is also provable. So that's what I was having on my last slides here, the case of Dirichlet functions. I was about to go through all the details. So now you look at the whole vector of Dirichlet functions attached to such a Galois group of a cyclotomic field. So you describe the whole vector of function of special values, so indexed by the characters of your Galois group, and by the same determinant formalism, it goes through. So the reason why you can prove anything is because you have these special value formulas, the limit formulas expressing the Dirichlet functions in terms of these cyclotomic units, and with lots of computation using Iwasawa theory, you prove this conjecture in the end. Even the two primary part, which involves some combinatorics, and I wasn't going to say more about that. And so the upshot is the case of Dirichlet functions, even this refined equivariant picture over the group ring of this cyclotomic Galois group here, where is it? This one again, is known. Yeah, so there is nothing open for this whole picture in the cyclotomic case or Dirichlet function case. And maybe I'll just stop at this point and take questions. Yeah. Yeah. I mean, you need some self-duality, I guess. Yeah, so that the M is the same as the M star 1, because remember in this functional equation we had the M star 1 here, but very often motives are self-dual, like the H1 of an elliptic curve is self-dual. In that case, you would expect the Riemann hypothesis. So, I mean, it's just a conjecture, but it's expected. Yeah. It's even expected much more generally. So if you remember this picture I had with automorphic forms at the beginning, there's many non-algebraic automorphic forms which don't correspond to motives. For these, we also expect the Riemann hypothesis. So it's even more general. Yeah. Oh yeah. Not really. Not really. No. The Baylis-Soulé vanishing conjecture is contained in that it would follow from the finite generation that I had in this conjecture mod infinity. Yeah. So it's implied by that.